I'm happy to be here today to present a little bit of the work that, together with different team members, we have been developing over the past time. And I think that he gave a very interesting introduction to what I'm going to be speaking about today. So we all know about blockchains here, and I am happy not to have to explain very much what this talk is going to be about. But you know that consensus is fundamental for the quality of of the way in which permissionless blockchains work. Consensus refers to the fact that, as you know, inside of these distributed systems, you have local copies of the whole ledger, and only when the local copies of the ledger stored in all the nodes that are running the protocol are the same, everybody is sure that the information is trustworthy. So the farther you are from this situation, the lower the quality of assurance that the permissionless blockchain gives you while it is working. And there is a challenge that the developers or the people that is designing new protocols have that is very hard to solve. Actually, this is the same thing that happens when people study economic systems, for example, or social systems, which is the conditions under which a protocol will be working are only simple to derive in very stylized conditions. We cannot know how the distributed network will look like when we deploy an instance of Bitcoin, for example. When people developed the Bitcoin protocol, and then other people started to run the nodes in a decentralized fashion, we cannot be very sure on which is the overlay topology of the peer-to-peer network. The same thing happens with Ethereum. And exactly because of this, when a protocol is designed, we always need to take into account a lot of very simplifying assumptions, like everybody does when developing a system in which people will start to behave in ways that the designers cannot control. And if you, for example, read the original paper by Satoshi Nakamoto in 2008, you will see that one of the things that he specifically makes mention of is the fact that he is considering that the time of transmission of the blocks within the peer-to-peer network is negligible, okay? And you see that this is a very strong assumption. And this is a very strong assumption, not so much if you think of a blockchain in which the interblock time is 10 minutes, and perhaps you have only 2 megabytes of block size limit. But after the communities start to behave, that all the open source communities start to behave always, and then you have a fork that derives to Bitcoin Cash, and then you have another one that derives from Bitcoin SV, you end up with some of these forks aiming at a maximum block size of 1 gigabyte. Okay? And then you see that now this original assumption, which was that the diffusion time is negligible, becomes harder to justify. And this also happens if you even think of something like Ethereum. In Ethereum, you have an interblock time of only 12 seconds. These 12 seconds, however, do not take into account the fact that the network has been continuously growing, and that you have tens of thousands of network nodes attached to the system. So you need that each block reaches these tens of thousands of nodes in only 12 seconds for the system to reach consensus in the interblock time. Moreover, and this is the last thing that we will consider, is the fact that also it is a simplifying assumption that it is always in the back of our minds, but we never reflect on them, is the agent behavior. For different reasons, in general, you assume that the agents are rational or the agents trying to follow the majority because this is the logical thing to do. If they want to maximize payoff or they just want to support the system, whatever. In general, also the way in which the agents behave inside of these protocols is always heavily simplified. And it is only under these conditions that you end up having well-derived working conditions for the protocols. Okay, all the protocols are designed basically under these simplifying assumptions. And the reason why we have this talk today is that eventually this is very let's say, limited. This is only the first step if you really, truly want to understand the way in which eventually the systems behave when they are deployed in a while. And also, these kind of approaches, as you will see, will allow us to better understand how people can also try to trick the system and make even more profits than what was supposed to happen as per the design of the systems. Okay. This is basically what I was saying before. Agent-based modeling is a kind of technique that allows us to expand the knowledge that we have with respect to the functioning of consensus protocols in blockchain-based systems, but also the robustness that they have in specific conditions. And I understand that it is a little bit the model. It's running out of steam. But in any case, proof-of-work-based systems are very, very interesting because they are the most genuinely permissionless blockchains that you can design. Anybody, in principle, we understand that eventually Bitcoin grew, etc., and all of them in general become, because of economic processes, become also closed by itself, but this is an emergent property. In principle, anybody can run their own nodes and start participating in the consensus. That's what makes them very interesting from the behavioral point of view. And I will explain two very simple things very shortly, hopefully. That is consensus in proof-of-work-based systems and how they rely actually on, or how people, the way in which they work assumes that there is symmetry of information, but actually how people can actually break this symmetry and make it to their own profit. And the basic idea is the following. In this system that is following the same way of depicting the system as it was, you have seen in the animation before, you have different nodes in a peer-to-peer network. Some nodes are colored, and what is happening here is that you see that there is an emblem on top of each one of the nodes. This emblem depicts which is the last block that was received by each one of the nodes in the network. Okay? So this system is not in consensus. Why? Because most of the local copies of the ledger inside of the nodes have the gray triangle at the end. There is a single node that is actually the miner of the blue node that was able to find the next block in the sequence, that is the blue diamond. The system is not in consensus, and what we would say always when we are thinking of a proof-of-work-based system is this node should immediately broadcast this blue diamond as soon as possible to its peers, the peers that it knows in the network, this yellow node and the other gray one, because then if he is able to diffuse this blue diamond block, he will receive the reward because there is a transaction inside of that block that contains the reward to the blue node. Okay, so this is strategically, and this is the most logical way of proceeding. But what happens if an agent deviates from this behavior? If an agent deviates from this behavior, is using one of the most traditional ways of exerting power on others in an economic system. That is, there is asymmetry of information in this case. At the point of the exist of this point in this snapshot, the blue node is the only one that knows the blue diamond. And therefore, if he has enough computational power, he can start mining and searching for the blue pentagon, which would be the next in the sequence, because he's the only one that knows the existence of the blue diamond. Okay? And if he does that, and this is the strategy called selfish mining, the question that always exists is, or that was for several years present, was, are we able to, is he going to profit from this strategy just by using it? Which means, after he mines a block, he holds it, starts mining the next one in a sequence, and if he identifies that someone else finds an alternate diamond in between, so a competing block at fourth level, then he will remain, he will broadcast immediately as well his own as a mitigation strategy. So when is this selfish mining strategy beneficial? And there is this original paper by Eyal and Sirer a long time ago, in which they found that under some, once again, under very strong simplification of the system, they were able to show that if at least they have 50%, so 25% of the mining power, this strategy becomes beneficial for them to develop. Okay, and what they concluded actually is that exactly because of this, you need even a larger pool of non-selfish miners in terms of computing power to make this strategy non-winning. Okay, and you see that from a logical point of view, the strategy is very simple. There was a lot of debate in the communities. A lot of people in the Bitcoin community say that this would never happen actually because this would be against the way in which the protocol works, and some Bitcoin derivatives would be happy to sue the people that tries to use this strategy. There is something very interesting, and this is a paper that we are about to publish in the next month in Scientific Reports, in the next couple of months in Scientific Reports, in which we actually tested whether people is using the selfish mining strategy, because there is something that is a clear signature of this strategy, which is that you have an overrepresentation of consecutive blocks by the same users. And what we identified is actually that in smaller blockchains in which the cost of selfish mining is low enough, like for example in Monacoin or Bitcoin Cash, the amount of selfish miners, there are constantly a few nodes that over time they continue to produce blocks in a row much more than what you would expect just as pure statistical significance. So what we did is, after doing this analysis, we did an agent-based model, and if I went through this introduction, it was I wanted to explain the logic of the model that we are using with through agents. Do this agent-based simulation, sorry. And the logic is the following. We have n nodes that we call miners, they are validators actually, and in the context of selfish mining, they can act selfish or honest. Each miner has a hashing power alpha, which is just a fraction of blocks that they can produce. And they follow the strategy that is given by what I said before. They have the longest chain rule. So if you receive a block and you are honest, you immediately accept it because your blockchain becomes longer. If you are a selfish miner, you only share blocks as per the strategy that I explained before. But the most important thing here is that we do not consider the agents to act in rounds nor anything, but we consider something that in different branches of science is very well known as a very efficient algorithm to model continuous time processes. That is the Gillespie algorithm. We have a peer-to-peer network that has whatever topology we want, but then what we consider is that there are a set of events that happen independently as Poisson processes. On the one hand, you have a process of block creation, which is basically the rate at which each one of the nodes in the network is able to produce new blocks. And then once a block is created, all those that received blocks, and therefore they have a longer chain with respect to the others, they propagate the blocks to their neighborhood. And this is the tau delay, is an important parameter because it tells how fast the blocks are going to be diffusing in the network. The Gillespie algorithm allows basically to compute all the set of events that are taking place inside of this system, and therefore we are able to measure a lot of things. Specifically in the case of selfish mining, what we find is actually that the larger the network delay is, which means a smaller value of lambda here, the more successful are selfish mining strategies inside of the system. The intuition is logical. The intuition is that the longer the time it takes for blocks to diffuse in the network, the more time I have to leverage on my strategy of withholding the blocks for myself. Even if I receive a competing block, it will take a long time to appear into another part of the network. Okay? So what we identify is actually that something like network delay plays a crucial role in the efficiency of a specific strategies. The other thing that we were studying later, and as well based on proof-of-work-based consensus, is what happens in absence of block rewards. In absence of block rewards, what happens, remember that all the proof-of-work-based systems have created this scheduled block reward production that halves every few thousands of blocks. And there is a point in time in which all these rewards are going to come only from transaction fees. So what we did is using exactly the same kind of agent-based model to try to understand which is the effect that this situation would have on the quality of the consensus. And without willing to go into much detail inside of this model, one thing that is very important is that actually the basic intuition is the following. If an agent wants to if I mine a block in which I use all the transactions that were inside of the mempool, because this is what maximizes my profit, and I send it to my peers in the network, I am not leaving any leftover of the rewards to the rest people that needs to mine. They need to wait for new transactions such that they that populate their mempool, such that the mempool such that they receive some reward because of the process of mining the new block. On the other side, if someone else, let's say Nicolò, creates an alternate block in which he uses not all the transactions like mine, like in mine block, but only half of the transactions in the block that were in the mempool, he's leaving. I have 3 minutes. Good. Negotiating. If he is only using half of the transactions that were inside of the mempool, what happens now is that whoever else is going to start mining the next block in the sequence has an incentive to use Nicolò's block and not mine, because he left half of the transaction fees inside of the mempool. And this actually creates a never-ending splitting story in which someone else may use only 25% of the transactions in the mempool, etc., etc., etc. And what we were doing in the once again using the same kind of methodological approach was using a situation in which each user, each miner inside of this system only will accept splitting of the transactions by the participants that created the previous block that they consider fair. It's based on an economic model called the Ultimatum Game. And once you do that and you run it inside of the system, what you identify is actually that you need a continuous stream of transactions that is fast enough for the mempool to be filled enough such that the rewards are accepted by the next block creators. But this is something very interesting because it also implies that the quality of the consensus continues deteriorates, because you always need transactions that otherwise would be already inside of previous blocks that are not confirmed simply because people want to split the reward with the next block creators. And this decreases the efficiency constantly of the consensus when you do not have block rewards. Okay. We were doing this kind of approach to analyze Ethereum consensus. There it is different because we were thinking what happens in proof-of-stake-based systems. But the basic idea is that we want to expand this work to strategic behavior as well in cases like, for example, maximum extractable value, like was explained today in Burak's presentation. The last thing that I wanted to say is this would not be possible without my team, but if you have papers to submit, please consider a Ledger. Ledger Journal is the first journal on cryptocurrencies and blockchain that appeared in 2016. I became chief editor this year, but it's not because of this. I think that the people that this... you can talk to me. No. Yeah, I think one thing that I like very much of this journal is that all the editorial team really cares about the quality of the papers that are published there. And they also follow a lot the story of all the submissions. And this is what has created a journal of very high quality. Thank you very much.